well, okay, at a super high level, superficial level, I help operate our portfolio companies. You know, you have, oh, shit.
To Sarajevo for a birthday party this summer.
Oh, nice.
But I hear it's awfully popular these days.
In the summer, yeah. All right.
Wait till it goes off.
All right, Sylvia, we good to go? Is my... All right. Let's get going. Sylvia says it's time to start. Hey, thank you all for coming. Can you hear me okay? I can hear myself just fine. All right. Cool. All right. So my name is Sasha. I'm with Playground Global. If you don't know, you're at Playground Global. We are an early stage venture fund. We love hard tech, robotics, AI, automation, next-gen computing, quantum computing, you name it. If it's hard, we love it. In the words of Peter Barrett, our CTO founding partner, we love to invest in technologies that are on the scale between improbable and impossible. And speaking of improbable to impossible, tonight is the right topic. You'll see, what Relativity is up to. But to give you a sneak peek what the company is about, let me start with a video. Rockets, huh? Yeah. Very cool. All right. So before I introduce our guest, just to let you know, if this is your first time at a RoboChat event, we do this on a regular basis about once a quarter. Well, we'd love to bring in experts that are world-class leaders in their field to discuss what they do, the future of their technologies, what challenges they're facing, and what their vision is for the future. So that's kind of frames also what we will talk about tonight. So in thinking, we wanted to do a space-themed RoboChat because that is the next frontier. And we were thinking, who is the biggest brain in the business? Who is a megastar, superstar who understands space better than others? So our first choice wasn't available, although he has a huge brain, he knows about space. And then we couldn't get him, but then maybe we could, because you never know who that guy really is. Because when you look at it and think about it, nobody has ever seen Jordan and Megamind in the same room. So, smart guys don't come around easy. So anyway, our special guest tonight, Jordan Noone, CTO, co-founder of Relativity Space. You will hear his story and what he does, but let's bring him to the stage. Thanks for joining us. All right. So we're not going to keep that head up there. It's enough to look at you. Just give you an idea what the 3D printers look like. All right. So, Jordan, I told you I would ask you this first because your story is so amazing. You are 28?
27.
27. Okay, you're not that old, yeah. All right, and we'll get to your story. It's just fascinating. There's so much interesting about you. And usually I like to start about, bring out something interesting about somebody, but that's what the next 45 minutes are about. So I really want to start with, tell me something boring about you. That's
No, there's plenty. It's hard to choose. I really like turtles. I think we've talked about turtles before. I was looking at some Reddit posts about a day or two ago that had 3D printed turtle shells for turtle rehabilitation. And then I thought that was really cool. And then the next post was like a turtle in like a knitted jacket. And this is what I do in my spare time. So people send me posts of
Wait, you knit or you collect turtles?
I look at turtle posts on Reddit.
Okay.
Then,
So there's a subreddit dedicated to turtles.
Oh, plenty.
That's not surprising, yeah.
more than one.
Yeah. Cool,
So
all right.
That's the one.
All right, so let's get to the interesting part. Okay, so rockets. So your story is amazing. You started at USC. Mm-hmm. What was your first rocket project and how did it end up? Hint, hint, it blew up probably.
Not the first one, but I started at USC when I was 17, so University of Southern California, and my first week there in my intro to aerospace class, the rocket propulsion lab came by, and they're a student group trying to be the first student group to fly a rocket to space, and so about 100 kilometers up, which is pretty high. And it was really a self-set goal. It wasn't something that was like a student competition or something that the administration set. It was a group of students who, 4 or 5 years before, went to the dean and said, we want to fly a rocket to space and want some lab space and some funding. And the dean said yes then, which was very fortuitous. And then I saw that group when I came to college. I never really thought of working on rockets before that. I actually oversaw the first 2 flight attempts to space then, so flying to about 150 kilometers. Youngest person, first student in the world to get FAA clearance to fly that high. Then the first 2 blew up very dramatically under my watch then, so got that experience through pretty early in my career. I think I had just turned 20 at that point that we flew the first one.
Still at USC, right?
Still at USC. Yeah. Then it was my junior year. I took over the lab. And yeah, that was my introduction to rockets. The group successfully flew last year, then on the 4th attempt. Then they had a lot of lessons learned in between,
right?
Up to about 110 kilometers up, which is more advanced than most countries' space programs. Then it's a small sounding rocket, so kind of 0 to Mach 7 in about 13 seconds. So you're flying about a mile per second, then which is rather aggressive, and especially for a student group. So yeah, they get attention from some groups when they fly that see things on the radar and get worried. But the most of that's past them now. All
right. So you graduated from USC. And then went to this little startup called SpaceX as an intern.
I went as an intern. I was 21 at the time. Then working on Cargo Dragon. Then so the Dragon spacecraft to take cargo up to the International Space Station. I was tasked with qualifying the propulsion system to fly on Falcon 9 version 1.1, which was starting with Flight 6. Then it was the first Dragon flight to go up on 1.1. So I got to touch the entire propulsion system when they're on my internship, and we actually had a big issue going into that flight. It flew the last day of my internship, and I had to cancel my conversion to full-time meeting. Then, which HR was very confused by, but I was in a room with the VPs, and there was an issue on one of the components I was qualifying, and we had a decision to make on if we flew or not. And that was flight 6 or 7 for SpaceX. And they fly 6 times a month now. But that was very early on for Falcon and Dragon, so there was some early stuff to work through.
That was 2014-ish?
This was 2014.
Yeah.
And I ended up converting to full time once the vehicle successfully flew to orbit and the prop system activated. But I don't think I would have went full time if we made the call there. That would have been a very different meeting.
Might not have been an option, right?
Right. So very early introduction, but very exciting to touch hardware, and that hardware flew that year.
Yeah. Okay. And then you converted to full time for all of 6 months.
I was there full time a little over a year.
Okay.
And so 2014 to end of 2015, and then I started working on the pad abort vehicle, which was the one to test the abort system on the capsule to take the astronauts to a safe location in the case there was an issue on the launch vehicle. And that vehicle successfully flew in May of 2015. Then, and I had hardware that I designed and tested on that one, and then we started the work to fully qualify the vehicle for flying, and that vehicle flew well after I left. It flew in early last year, the DM1 mission, Demo 1, to the International Space Station, and I had hardware that I designed that flew to station.
You know, what's so interesting about this story in general, you know, so you were by then 22, 23?
I had
Okay.
I had just turned
Early
20.
20s.
Yeah, I was 22 at the time that
Right.
pad aboard and DM1.
So for a while, I ran engineering at Cruise Automation, self-driving car company. And we looked at a theme that would motivate the people. How do we, you know, it's a really long, drawn-out R&D project to put these cars and fleets of cars on the road. So I came up with the theme of calling it like a space program. You know, we called the ultimate goal an Apollo launch. We have some cruise people here, actually. You know, I see them smiling because they're still working on it. But what's really interesting is that, you know, when I researched the Apollo program, I bought this book that I recommend to everybody called The Apollo Challenge. So many processes about engineering, running engineering projects, innovation, hard problems were tackled during the Apollo program. And I found some amazing quotes from engineers who worked on that program. They were all in their early 20s, early to mid 20s. Because everybody who knew anything about space didn't want to work on it. It was impossible. Like, who wants to do that? You know, no, we've been there, done that. You know, don't go there except, you know, 20-something. Sure, I'll work on that. You know, what's the worst that can happen? I launch a rocket or I launch a self-driving car. So, you know, I see a lot of parallels in SpaceX and with what you guys are doing. All right. So, when did you meet Tim, your co-founder?
I met him in the Rocket Lab, so at USC.
Oh, at USC, okay. But he went a different path. He went to Blue Origin.
That's right. He went to Blue after graduating. He's about 2 years older than me. So he graduated. I kept running the lab, but we stayed in touch.
All right. So at Blue Origin, he dabbled in 3D printing, you know, for specific parts, this and that. So how did you guys decide that was the future of aerospace?
A lot of it was seeing success on printing at a small scale. So SpaceX's Crew Dragon actually has some of the first early 3D printed components to fly the Super Draco engines themselves. And those are smaller scale. So the 3D printing we're talking about right now that we were seeing at these former companies was about 1 cubic foot size, so kind of desktop ornament size objects. And there was a lot that we really liked about it as far as how quickly you could make it, how easy it was to change things, how it changed kind of the supply chain and the manufacturing flow. But no one was really bullish on getting an entire rocket printed. And some of the early conversations with me and Tim were, as we would hang out, we'd go to Seattle, we'd hike around, and you'd be talking about it. It's like, yeah, printing's amazing, but no one wants to adopt it. And we saw a huge potential in the technology then and started asking the questions, well, why don't people want to adopt it? And what's the thing stopping that adoption? Then, but also how do you scale it up to an entire product? Then, and not just a one piece part on a 100,000 part vehicle. Then, and that's where the ideas really started to formulate on, could you make a printer big enough to make a very large section of the rocket? Then, and here comes a napkin, and you start, doing some calculations on how quickly can you melt this much metal, and do the economics work out that you can make a printer big enough to do this and print it fast enough to have a reasonable business case. Then, and everything was looking good. Then on that, so we decided to both quit and start a company.
Nice. And then Tim was bored one night and shot off an email to some guy to ask for money.
Yeah, our early days, and both of us went to engineering school, no business classes, no business training. In that way, we'd both kind of managed people within the student group then and had to do various things on FAA regulation and manufacturing a complex operation of getting 100 people to the middle of Black Rock Desert and flying a rocket without the Air Force trying to shoot it down. Then and kind of the challenges around that as young individuals, but never ran an organization before.
Right.
So we start doing reading, and we stumble upon, you do what kind of I'd say anyone would do at this point, and it's like how to do a startup on the internet. And the two things that came up were Mark Cuban's name as far as go on Shark Tank, which we never did. We didn't go on Shark Tank. Then the second one was apply to Y Combinator. Then those were like the two routes to fundraising success. Then so we tried some combinations of Mark and Cuban and abbreviations of that at gmail.com. Then which it's anyone could put together what his email address is with enough tries. Then and said space is sexy, 3D printing a rocket, and
that was the subject line.
That was the subject line.
Yeah.
Then I still have the email. We should print it out at some point. Then. And then explained, why it made sense in a couple sentences. As far as, if you 3D print everything, you can change it very quickly. It lowers the cost. People want to buy it. Then, and we were fundraising, this much money at this valuation. And he responds and he says, he has a couple questions, and then we answer them, and he responds again. He says, sure. Then so easy, $500,000 secured. That was good. And then we also applied to Y Combinator, which I don't think we realized how at the time prestigious they were and how much they'd play out as a very valuable partner for our growth. But we got into the Y Combinator program as well. And then actually was a very short phase that probably could have imploded us, where we didn't realize we could get both investors to agree on a set of terms. Then we just had no experience in this. Then on a set of terms, so we thought we had to choose one or the other. Then where Mark was offering more money, but Y Combinator had generally a bigger resource pool and bigger reputation in the valley here. And then we talked to enough people, and they were like, yeah, you're silly, just tell their lawyers to talk, and you'll get through it. So by kind of week 2 of the company, we'd figured both of those out. Then, and we had $620,000 in the bank, and we were needed to move to San Francisco for YC. Then, but from the paper idea, we got to that point in 2 weeks, and we had to incorporate and get a bank account, and talk to lawyers, and all kind of the fun steps in between. But that was again kind of days 1 to 10.
All right, so I don't know how much learning there is for other startup founders, like sending a cold email to get $500,000. It's not a proven path.
I'd say it very much it misleaded us on how easy fundraising was.
Right.
Then it was like, oh, this is easy. You just send a couple emails and fill out a form. And it got a little harder after that, but we're clearly still putting along.
Well, full disclosure, we're an investor in Relativity space, Playground Global. So
it was more than an application.
Yeah. You have some A-listers also that are investors.
A-listers.
Hollywood A-listers.
Oh yeah.
And I don't mean Jory Bell and
Jory's.
Is he here?
Yeah, Jory's right.
There he is.
Jory's on our board.
Yeah, Jory.
If you have any questions on what it's like to manage us, then we're tough. But no, there's a couple.
Yeah.
Jared Leto's. There's some like 30 Seconds to Mars references that sometimes come up. Then, but yeah, there's a variety.
I also liked when I visited your facility, the little strip mall where you are. Oh, right there is Bruno Mars' studio. Oh, over there is Snoop Dogg. Oh, that's Keanu Reeves' motorcycle. This is where he works out. Oh, this is, I forget who else. It's like crazy.
Yeah, if you've ever been to LA, the west side starts kind of west of the 405. Then in everything east of the 405 is you have a couple miles of kind of like don't go there at night. Then, but the 1 block west of the 405 that is Inglewood, then it's a very small corner most people don't know about. We are in a section near Randy's Donuts, which is the big donut that's been in like Iron Man and a bunch of the Avengers movies. Then it's like the local landmark is the big donut. We are in a business park that it's us, Snoop Dogg's recording studio, Bruno Mars's recording studio, and then Keanu's stuntman training gym, which has like Halle Berry trains there, Taylor Swift, Jason Statham. It's a variety pack. And so it's an up and coming part of Inglewood, but we are moving. We just signed a new headquarters about 2 weeks ago.
Yeah, you don't want to be close to them, yeah. All right. So let's go into like real tech stuff now. Yeah. So I mean, to 3D print a rocket, there is the printer. There's all the rocket stuff. There's all the material sciences, all the software. So let's break that down and talk about each one. So 3D printing, hardware and software, the innovation you had to do there at this grand scale. Talk about that a little bit.
Yeah, and we'll bring back a little bit to the company vision really quick, which was to 3D print an entire rocket. Then, so it was kind of from the ground up, how do you build not only the product but the company to support this effort? And that was a lot of the conclusions from the early days, is that there's a lot of inertia not only on the tech, there were tech developments needed in order to scale the technology, but also culturally. Then that people tend to not want to adopt the tech because of certain either the philosophy of the design process that they're established companies, or that there's enough, kind of more established people who are like, you would never introduce this into something like a rocket because it's this new scary thing. And it's a very risk-averse industry. So kind of, again, going to the ground floor and saying, we're going to print everything by default and convince us otherwise. Then if it's something that makes sense to make traditionally. Then, so that's kind of where the premise of the company came from. That does wrap in with our long-term vision of 3D printing a rocket on Mars. We want to be the first company to 3D print something on another planet. And we see a direct path between the tech today and there, where today we're using the tech to support commercial telecoms, imaging, a variety of applications here on Earth. But it's that same technology you'd want with a civilization off planet, then to be printing things to support, them becoming more self-sustaining. You're not sending us 2 of every spare part from Earth. You're sending a printer then, and you can print those parts as you need them, and it's much more efficient.
A spool of aluminum coil and a printer.
Exactly.
That's it.
Exactly, and eventually to be able to process that raw material on
Right.
on the locally as well.
By the way, just before, so if you guys missed it, there is a portion of a 3D printed tank right next to the piano at the entrance. So that's their tank.
And a part of the premise of the company, I was talking about the kind of the 1 cubic foot size parts, the desktop ornaments. Then that other people really are starting to love, and they're across aerospace. They're definitely getting good adoption, at least in kind of single piece volumes at that scale. But we wanted to print an entire rocket, and the rockets we make, they're 7-foot diameter and 105 feet tall. Then we print them in a couple sections today, but it involved making the world's largest metal 3D printers. Then that's what you saw in the video. We have 4 of them at our headquarters. There was a quick time lapse of seeing them print all together. Then we'll have 9 of those online this year, so really starting to go into a much more production-oriented state with them. The current ones go to about 15 feet tall, so about, I'd say up to where the kind of the ceiling girders are in here. Then we have 2 coming online this year that go up to 30 feet tall, so quite big in size, and those can do up to about 12-foot diameter. So by far the world's largest printers. And that was tech that we had to develop from scratch.
Yeah.
So a lot of the early days for us was me developing the printing process, kind of the core of the printing tech. Then we demonstrated that before our Series A fundraise back in 2016. And then we built the first full-size tank, which represents the upper stage on our vehicle, so 7-foot diameter, about 14 feet tall, which was the milestone that kicked off the Series B, which was the round that Playground led a couple years ago. But in order to scale that tech, it was quite a challenge.
Yep.
Then printing is a very complex process where you're melting metal and real time having to control and tune that to get a very consistent process, especially for aerospace applications. And in scaling the tech from the smaller scale, so again, kind of the 1 cubic foot scale, to small building size, then a lot of things change. And there's a lot of things people stuck to architecturally in the smaller printers because they're easier to control, and there's people that are pushing the tech and complexity that way. But we wanted to go for scale. And in order to scale it, you had to change a lot architecturally within the printers, which the main way we resolved a lot of those changes was doing real-time control on the printing process. So very much going into the software stack, some of the sensors that are used during the printing process in order to get that controllability at that scale and to know that the part coming out of the printer is one that you would want to use for an aerospace application. Which has been rather tricky in order to do. And we have a team that's full of data scientists, roboticists, the mechanical engineers doing the design, full stack software engineers for all the elements between the GUIs that the operators use all the way down to the infrastructure that does the real-time compute and deploying all that
So
stuff.
just that is a company in itself, the technical challenge and everything to do.
It is, just the printers themselves is one of the challenges, but also having the printer side of the company operate alongside the rocket side. Because they're both developing in parallel, right? That in order to make your rocket printable, there's a lot that you have to change on it. Yep. And you're developing the printers in parallel. So we have to figure out that resource balance as far as if there's something the rocket wants, then that isn't printable, then do we push back on the rocket on a performance side? Do we invest in getting more features out of the printers and more capability there? And sometimes that requires pushing back on the rockets and pushing them to more of a non-traditional design. And within aerospace, there's actually a lot of very classic conventions where you don't fully understand why something works, but you flew it and it worked, so you're going to do it again. So pushing back on that and doing something non-traditional can be really kind of scary for those engineers. And as a company, you're going into more of the unknowns. And that can be a challenge as well. So it's a little bit of a tough road mapping effort as far as getting that balance right to be in to use capital efficiency going.
But even the seemingly simple things as even moving the wire from the coil to the print head at a steady speed without it getting stuck, you had to do a lot of innovation there too.
Yeah, and I could dive into any of the areas, but we're feeding wire at a couple inches per second into this molten melt pool while you're melting it and then moving the heads to keep that wall fusing. And even those feed systems, they're full of consumables that wear down because you're having metal on metal contact where you're feeding this metal wire multiple inches per second for days. And even in like automotive lines, there's been a lot of developments in making sure that those systems don't break down, they don't have debris forming in them, but they generally have downtime at some point.
Right.
But with these systems, we've gone from, even robots that are meant for cycles from the, seconds to minutes range, to now we're running these for weeks.
Yeah.
And so everything's really stressed in what gets used there in a process that doesn't like to turn off. Then, your part is hot, it's warmed up to a certain size, you're depositing in a specific location, and now you stop the machine and you have to do a cold start where your wall's now moved a couple inches away, and you're having to live compensate for not only that shrinkage, but then also as the part grows, that you keep that wall very consistent. Because these walls, even though they're at a 7-foot diameter, the walls may be, at locations an 1/8 inch thick. And so it's a very flimsy part that moves around a lot, and as those thermal transients go through it, as you restart it, you can have that wall move around a couple inches, and keeping that wall consistent, it's a real-time challenge.
Yeah. All right, let's talk about the engine and the propulsion system design. Can we, here, I'll do it, or you do it.
I can.
Yeah, why don't you do it? Show what we have, what you have.
This is one of our engines here, so the fully printed engine stack. There's 9 of these on the bottom of the rocket, so each one generates about 23,000 pounds of thrust. Then, so significant amount of thrust for their size. The vehicle we fly is about 170,000 pounds at takeoff. Then, but we fully 3D print these. These are made of the components that are kind of the desktop ornament size that I keep talking about, the 1 cubic foot. Some of these are a little bigger than that, but fully designed in-house. They're liquid methane, liquid oxygen fueled. There's turbo pumps on these. You'll see the objects with kind of the rectangular tubes coming up off them. Those are the turbine exhausts from the turbo pumps. So actually using propellant similar to how a turbocharger would be running off the exhaust of a car. This is running essentially off the exhaust of the engine in order to run the turbine, in order to run the pumps, and pressurize the propellant going into the vehicle. So you actually carry the propellant at a very low pressure and pressurize it up, about 1,000 psi within the pumps in order to feed that into the engine. There's a lot on the parts here that you actually can't see because they're printed. There's a significant amount of complexity on the inside of the combustion chamber, the injector, and those are a lot of the things that we really saw promise in with the printing, is that you can get a huge amount of complexity with no mechanical labor, no effort there. All of the complexity is pushed into software. So if we have a change that we want on the vehicle or the engine itself, you do a software change and then you print it. And we can get the injectors on these, one of the more complex sections, in about 4 days from the powder bed printers. Then where traditionally that could take, a year to get, especially with a new version.
So is that the equivalent of what you testified at your site in Mississippi?
Mm-hmm. Yeah, there was one of these that was on the screen during the engine firings there. This is one of many. We've probably made close to 20 different iterations of these as far as the full stack in the history of the company. Then we're getting ready to enter qualification on the engine going into first flight of our vehicles next year. So starting to lock down the engine configuration, the hardware, and then have 9 of these, all firing together on the first stage of the rocket.
All right, well, it's a good time to talk about the propellant too, because you're innovating there as well. Mm-hmm. That's not the propellant.
This is not. Some people do use water. One of our customers, they hand out water bottles that say this is rocket fuel. I have one. But on the propellant, to go back into some of the premise of why the printing made sense, how to think about the company was reducing part count, reducing complexity on the vehicles, and that's generally not something you'll hear from an aerospace company. Then is to have part count reduction as the goal of the design, then in one of the things you optimize for. But from our perspective, how this played out, as the printers get bigger, as you print more and more of the vehicle, you dramatically lower part count. And that gives you operational efficiency in a lot of ways where you're not training technicians on this huge variety of parts. You don't have these huge ERP systems. We still have one, but it's much more simple than something for a much bigger company. Just the number of things you're tracking, the complexity of your supply chain, the complexity of all the financial planning when you have these hundreds of thousands of parts that are all different. And so we went very much for simplicity. And one of the ways we did that was architecturally on the vehicle, then including the propellant choice, where if you use two propellants, such as the liquid methane, liquid oxygen mix that are of similar temperature, their flow rates are similar enough that you can use, let's say, the same valve in the oxygen system as the methane system, you can cut your components in half, as far as you now have half the number of valves you would if you used a hydrogen oxygen system or an RP1 oxygen system. And so we went with that from the beginning, is thinking about how to lower the complexity of these so that you can move very quickly, especially as you change them. Because when you have this 100,000 part vehicle, then in this huge organization, changing one thing can trickle and propagate in ways that is really hard to account for, is very expensive. And we wanted that very lean maneuverability, including on kind of the piece part side, even going down to the valve level.
But what's the trade-off there? I mean, it's technically much more challenging with liquid oxygen and methane, right? Otherwise, everybody would go there.
It is the direction the industry is going in, but it is significantly less mature in directions. And that goes back into some of the aerospace side of things, that certain propellant combinations have a huge kind of database or publicly available information on some of the properties that are actually really hard to characterize. Then as far as how much heat does the coolant that cools the combustion chamber, because we actually cool it with the propellant, then it's flowing through a jacket on the outside of the engine, then that you can't see because it's all printed on the inside. Then, but how well does that pick up heat? And it's one of those things that sounds like, oh, you just have a lookup table for it somewhere, and like someone's characterized it well enough. Then, but the temperatures and pressures that these operate at, they're actually really not characterized well. So there's a lot of testing and anchoring to do that's done on the test stand, where you'll throw an engine on the test stand and see how much heat the combustion chamber picks up there, and then fine-tune the design. And that actually leans well towards the printing, because you can stick something on the test stand, test it, not analyze it as thoroughly as perhaps someone else needs to, because you can have a new version on there in a week or two. Then, so it lowers the barrier to entry to using some of those combinations. But it also is very difficult on an engine development side, because there's a lot of empirical relations in aerospace, especially combustion chamber and injector design. And a lot of stuff you just kind of have to learn on the fly, which is definitely a challenge. It's been a challenge for the whole engine campaign.
All right, so we're walking through the different components, what it takes to build a rocket, starting with the 3D printer. So let's talk about avionics, software and hardware.
Okay.
You have to do that in-house as well.
We do. We do our own flight software then, and that has to be a real-time control system for doing all of the feedback and control of the vehicle. There's a lot on an FAA licensing side that goes into the software. Then, and that goes into the main regulatory body that looks at us, which is the FAA, and making sure you don't accidentally send your rocket on a trajectory that would, let's say, land on a house. Then, and if it does look like that's going to happen, that it can terminate its own flight, which is essentially shutting itself off, or in some cases you do have to destructively terminate the vehicle during the flight, and then making sure that debris doesn't fall on a house. Then it's a challenge. So that software, the whole stack on a flight software side is built in-house. And, but also on the hardware side, we hit challenges that other companies don't, and that's because of the flexibility we want as a company. And so if you can change the physical size of the rocket, on demand, then it was a great step. Then you need the rest of the avionics and electronics to scale that quickly as well. And traditionally, avionics systems are not built up that you can have a new design out in 30 days. But we needed to do that. So we presented that challenge to our avionics team, and the way that they solved that was going to a distributed modular setup on the avionics. So rather than having what's called traditional, like a remote in-out box, which handles all of the sensor feedback, all the valve commands, and has these huge harnesses running up and down the vehicle, then we made all of that modular. So there's still a flight computer, then we get those off the shelf. There's a bunch of switching equipment that we get off the shelf from some of the more traditional aerospace vendors. But all of these remote in-out boxes we develop. And there are some real challenges with it on redundancy, on fault tolerance with that system. But once you have this distributed setup that can, let's say each of these boxes do 2 valve commands and have sensor feedback from 2 different sensors, now you just place these all over the vehicle and you route one, essentially a CAN bus through everything else. And if you change the size of your vehicle, you have one line that you're rerouting, which is much easier, and it has a common connector everywhere. Then so very easy to scale rather than every single box having a different type of connector on it, which aerospace will often do in the name of performance. But now you have 200 different part numbers of connectors, one your 18 pin, your 17 pin, your 22 pin because someone wanted to go there. And then it's super hard to change, and you have to have equipment to handle all of this and part tracking to handle all of this, then a separate bin and a separate inventory area to handle each of these differently, and it compounds in this really terrible way that it's in the name of performance, but it makes this company an operational nightmare if you do it that way.
So do you have to develop a simulation environment for all this? Because obviously you can't test it in the real world.
There is significant testing of the software then, so as far as replicating the environments, and it goes all the way to what's called, the industry calls it HITL, or hardware in the loop testing. I don't know how much that word gets outside of.
It's common, yeah.
And then for testing all the hardware, and that is required on an FAA side because you're trying to understand specific interactions with the specific inductance of this valve, then and how that propagates back through your systems and how that relays into your controls, because you really don't want the software acting up during flight. Then in the side that works the termination side, the flight termination side has to go through very, very rigorous testing there, not only on a HITL side, but on things like vibration testing, shock testing, whatnot, that you have to demonstrate that this can do all of the real-time compute and not have two things start getting too close or touching or shorting during, let's say, a very high vibration environment. Then in the vibration environment on these vehicles is extremely high.
All right, so you have the printer, materials, engine, avionics, software, hardware, redundancy, everything. You have to build significant back-end infrastructure and tools to keep track of all that and the interdependencies and to keep everybody on track. So talk about that too. That's like an entirely different field now.
Yeah, I'll touch on maybe two or three areas here. The first is on the back end for the printers. Then that's been a setup that's been rather challenging to scale. Scale that architecture as we've gone from one printer, operating for barely 5 minutes without it shutting itself down and freaking out or catching on fire. Then they don't catch on fire that often, but only 3 or 4 times. But know that there's a significant amount of data going through that. Some of the cameras we use are 10 gigabit per second cameras. Then, and we're processing that data in real time to do computer vision on them in their high dynamic range, melt pool cameras. So you're looking very, very close, but very high resolution for understanding what's going on in the melt pool and understanding that in real time so that you can control and tune that. And that's the level of fidelity we need on some of the features we do. And that has involved, a significant amount on, how do I phrase it, as we've grown, there's tiering databases, there's all the real-time side as far as how do we make this setup work, not only 24/7 for 3 weeks, then but an architecture that can handle that much data. Then that's been a challenge. Some of the stuff even on approaching production where you have more and more people working on the same product. And we've gone from one software developer working on these to, let's say, 10 at once. That before, again, when we couldn't keep the printers on for 5 minutes, no one cared about configuration management. It's go on the machine and edit this file, and see what happens, and who cares if it's committed because it's probably not going to work.
Right.
And then all of a sudden you have 10 people, some of which are with the machine, some people are not. Everyone's pushing things. And we went through this period over the course of a year. Then from barely able to keep them on to slowly churning it. What are the things causing them to turn off? Then or preventing us from wanting to keep them running longer. Then to now, we had our first print. It was probably even last year that lasted longer than a day. This was last year. The first print to last longer than a day, at once. Then without us having to interrupt it. But now this is a production environment. Then where it's running, you have to monitor it, you have to track it. You need to know what configuration was installed because everyone's pushing things. You need to know what's actually on there. And still the developer's favorite environment is to go to the machine and log into one of the controllers and edit the file. Then you don't even have a good way to track what's on that machine. And then so that level on an infrastructure side has been, it's something we're still going through today is.
Because these robots have never seen anybody use them with that much change happening on an hourly basis.
Yeah, we use Kuka robots because
Right.
we try not to reinvent the wheel on the robot controller. Then there is stuff we've had to really tweak on them in order to get them to run for that long. So we stream commands to them rather than running off of the actual robot controller. Then, but the Kara C4, which is the KUKA standard controller, then is not something meant, one, to have change on it, but two, it does not like handling configuration management. The way you push changes to it it's a huge pain. Then, and that's by far kind of the most Wild West part of the stack, and it's the most critical because it's the endpoint for what everything's talking to. Then, and sometimes you'll mysteriously see that something changed on it, and we have no traceability on that entire part of the stack. And so we really have to have good diligence from the engineers on like, please don't log into the controller and change something. Then, because no one will ever know what happened. Then, and you'll realize like 6 months later that like you've been having issues because there's a bit flip.
You can't go to KUKA and say, hey, can you implement this change control for us?
They've mentioned, like I've talked to a variety of the people there, and I think they know it's a problem then, but I haven't yet seen a solution that's fairly viable yet. Then, but I mean, that's perhaps debatable. But no, so that part of the stack on rapidly maturing from a pure R&D to a production environment, sometimes at the same time where we'll switch a machine, like one of the big printers, from, this is a production print that's flying to space next year, and then the next one is we're going to try some things.
Right.
Then that it's very different, but you need the same machine to be configured, one day for R&D and one day for spaceflight. And that's a challenge as well as far as that level of configurability. Then where you can dynamically change between those kinds of styles. And it's even a challenge on a team side where, again, the engineers who did all the hard work to get these things running into a production state are now told they can't edit the software because it's a production machine and they're not allowed to change anything. So there's a lot of dynamics there as far as growing that software development campaign to a production state while simultaneously doing R&D.
Right.
And it's a pain from pretty much every perspective. And then some of the software we do is software and infrastructure, things like out at the propulsion test site. Then where you are entering a test campaign, then with an engine, it's safety critical. You don't want to accidentally send a command to the wrong valve. Then, or when someone's, let's say, operating on the test stand. So a lot of levels of controls, a lot of levels of checks to make sure that the system is operating correctly, and we've still had our challenges there. But
but is there innovation there? I would think people might have figured that out because people have been testing engines for a long time.
The big challenge there on innovation that I'd say is it doesn't get the attention it needs early on. Then where, let's say, the software stack running the test site, often at rocket companies, right? So even the software that runs like the launch site. Then it's sometimes viewed as like second or third tier software. Like you're either the flight software people or you're the stuff that runs on the ground. Then, and that has its own challenges kind of culturally. But one of the things is that you now have a separate software team developing the stack that needs to talk to the rocket at the test site, a separate team working on a set that has to, the stack that has to talk to the rocket at the launch pad, and then all of, let's say, the stuff that's talking to the vehicle while it's flying. Then, and all of three of those tend to be different because they have to be activated at different times during the development. The test site's been active, since 2016. We hired our first flight software person last year. Then, so you have that stack coming together multiple years before you ever have a flight software architecture. But you want to be at an end state, kind of into development where those stacks don't differ because you don't want to be supporting multiple teams working on talking to the same product in different ways. Yep. Then, but again, you're starting that development years earlier before the full flight software team exists. So we did put a lot of intentionality into how to keep that consistent and reduce the size of the team as the company matured into kind of the areas of the product we had to work on. And we've had some lessons there where I've gone back and forth that was actually the right thing to do, in the sense that now that we're trying to maintain commonality between all three functions, then when we do need a change in any one of them, we have to kind of activate all the parties. So
affects everybody, yeah.
It affects everybody, so you actually can't move nimbly, but you were doing it in the name of keeping the team small. Mm-hmm. Then where I think there could have been a different optimum that it's not the right time to turn the boat, where having multiple nimble teams working in parallel and on certain things having similarity but certain things not, we actually would have done it faster.
All right, so before we go into the business side of this, are any other modules that we missed? What it takes to put it together?
On the design side, one thing to talk about that's interesting is we've compressed the manufacturing time significantly. That was a lot of the part count reduction, throw everything in a printer. Our goal is to print the rockets from starting a print to flying in 60 days. Then we're not there yet, but that's the goal we want to drive towards. Then, but that actually adds a lot of challenges on your design toolkit, even on, let's say, mechanical design. then that some of these parts are very complex, right? Especially on the insides. On the outside they're cool too, but the insides are orders of magnitude more complex than what we're seeing on the outside here. But that means that your design toolkit's actually really important. Let's say on a CAD side, so the actual mechanical design. If it takes, let's say, 2 weeks to print the injector, or let's say 1 week to print the injector, then so 7 days. It actually takes some time in order to regenerate the CAD model and get the visuals right. It can take a day to regenerate the CAD model with today's CAD tools. Then because of that level of complexity. So if you want to change one thing on the injector, you click a couple of buttons and then you say go, and it takes a week, or not a week, a day to make sure that that change formed correctly on the CAD model. And that's a challenge we're starting to face today, where we've actually made the printed parts so complex that we don't want to change them because the CAD models are such a pain to work with. So we've hit kind of like a different part of the stack, being the pain point, where we're starting to evaluate how to turn that CAD toolkit set into something much more tuned for this complex of a product. Then where it actually may not make sense for someone to be using the GUI, and it actually goes back to some of the old school CAD ways of like the 70s and 80s, where you're actually doing it, you're building it up command line based. Then because there's no way for someone to go through and click all these features and do what you want and verify it was good. So actually it reverts the CAD platforms away, but it also then needs a skill set which is not that common today, which is designers who can do significant programming. And that's just not the most common skill set there. So it focuses what part of the design stack needs attention once your manufacturing is compressed so much. And I think that surprised us a little bit in how, or the lack of readiness in some of the commercial packages for this coming down the pipeline.
You're pushing limits across the board.
Right. Yeah, no, and even for the designer's sanity, when you have a part like this and it has 800 fillets on it, and in there they're clicking every single one by one, or trying to get the auto fillet tool to filter that out correctly. Then you try to get it correct, and then you auto fill it, and then it gets one of them wrong. And it took a day to get there, and then it's you change that. So that part's it's an interesting caveat, and it's giving us attention on how do we want to push some of our vendors, or perhaps bring up some of that stuff in-house eventually. And it's not, I don't want to recreate the CAD environment. I want to leverage some of the other ones. But it's not the direction they've been pushed historically. Right. And engineers aren't necessarily trained for that change.
So we're going to cover one more topic, the business case and the vision for the company, but then we're going to get into audience questions. There's a microphone there. If anybody's interested, eventually just line up and we'll take audience questions. So all right, so the business case of 3D printing rockets. Your vision is raw materials and design to launch in 60 days, and eventually do all that on Mars. All right, so tell me why that makes business sense compared to how other people are doing it, SpaceX, reusing rockets versus 3D printing them.
Yeah, so rockets and aerospace in general is a very labor-driven industry as far as where the cost comes from. And so the question is, how do you get that labor cost lower, and where does it come from? And a lot of it's mechanical assembly. It's, if you change something, you're retraining technicians, you're retraining quality assurance, you're using you're updating the work order system and having people writing instructions there. Then you're having designers teach the manufacturing engineers the right way to get the right things right within the part, which may not be obvious due to just the level of detail that goes down to. Then, and then all of the operations to support that, where every single part is a snowflake, and has a snowflake supply chain as far as this exotic alloy here, this exotic alloy there, and then all of a sudden you have a dedicated supply chain person for every single part in this entire rocket. Then it compounds terribly, because it's diminishing returns on the organization size, and that's how you go from wanting to be a 300-person company to then you're all of a sudden 10,000. Then because this compounds so poorly. And so we kind of looked at that and said, if you introduce the 3D printing, you lower the part count, you restrict the alloy types. You'll notice everything out here, all of the engine parts are made from the same nickel alloy. Then, and it's a nice high temperature, high performance nickel alloy that the engineers get by default. Then so they get the nice material by default because we order it in bulk, then it's just available. They have less even, I'd say, decision making to go through then, because they already have the nice material for cheap. Then they don't have to do the cost trade there.
Right.
Then, so you start to get these benefits like that, and then all of a sudden you're like, okay, we don't even need a supply chain department because you order 2 materials. Then, and that, the engineers can handle that on their own. And then, areas like that where you lower the operational overhead, and then you lower the pain in switching costs as far as iteration ability. That aerospace is really tough because you learn a lot when you fly, you learn a lot when you test. You make such a complex product, you don't want to change it. Then because the manufacturing line is so expensive to make, then, and that's kind of my one-sentence history story of aerospace is too complex to want to change it. Then, and you hit huge amounts of stagnation then in the industry where this super cool thing happened, and then that was the cool thing for the next 40 years. And that's, space shuttle main engine, things like that. So it was really drilling down into how to change that iteration speed. So you can get new products out. You can change to things, or change to account for things you saw on the test stand, on the launch pad. Then, because those are huge drivers of cost. When you have a rocket on the launch pad, you're testing it, and all of a sudden you realize that something on it's either broken or you don't want to fly. Is how do you activate this organization to change this thing that every day you're burning, $1 million because this thing's sitting on the launch pad? Then it involves a huge amount of people. And that's the way people have solved it before, or companies have solved it before, and we wanted to solve it through technology. Then lower the part count, lower the complexity, lower the supply chain needs, then provide, what I'd say is an even more fun engineering environment where you can design a part and then have it 4 days later rather than waiting a year. Then that's no fun when you have to wait a year to get the thing you made or you designed. And then costs start coming down. Yeah. And because of all the operational overhead reduction, and then to our customers, they don't care if you have the super high performance part. Then, like some of the printing things and why it's been hard to adopt is that there are things that are different. Then let's say this part is rougher than your machined part, so it'll have worse pressure drop or worse flow performance. Then, so certain people won't want to adopt it then because it's not the high performing thing. But for us, if we can lower costs, the customer doesn't care if you're accounting for your high pressure drop with just more pump power, then which is the way that we solve it. Then they care about cost at the end of the day, even if you have like this kind of chubby vehicle for its payload.
So you're balancing speed, cost, quality. We'll talk about quality, the impact of all this.
The quality review actually goes up because you're paying attention to so many fewer things that it's easier to scale that organization. Then, and a lot of the issues in aerospace come from mechanical assembly errors, where you have someone who's supposed to tighten a bolt to this torque, and they tighten it to another torque. Then, or you have them drop something because they have 800 washers to put together on this part, because 800 bolts, and the 800 bolts are all of 10 different sizes because no one likes commonality there in the industry. So all of a sudden, like, you have all these just moving parts around. Then, and a lot of interaction with people, and again, the people part is hard, and there's only so many good technicians in aerospace. The scaling problem is really hard as well there. So you push all of that into software. Then you get rid of significant amounts of the mechanical labor effort of the amount of touch points on the vehicle. And then your quality goes up through that. Even if each individual part is not necessarily as high of strength.
That's an interesting point. Individual parts might be lower quality, but assembled together, they're higher quality than something made out of 1,000 parts.
Right, like failures in aerospace don't generally happen then because you designed the part wrong and it's not as strong as you wanted. Yep. Then they happen because someone incorrectly installed something, or something got nicked because you had this cable against this beam that hasn't been deburred correctly, and all of a sudden you scratch through the insulation. Like, that's why things come down.
Right.
Then it's not because of the part not matching its specification. Then that's extremely, extremely rare.
So if there are so many advantages to 3D printing rockets, why isn't anybody else doing it?
Part of the challenge is, I'd say, in designing the product to be printed, that there's still that part then where there's a lot you have to change in order to make it printed, and there's a lot of inertia against that. Okay. Let's say even some of the stuff I was talking about on designing the cooling channels. Right, that people, and a lot of those correlations out there I was talking about in the empirical relations, you need this perfectly smooth surface. Then, in order to match their correlations, well, we don't have a perfectly smooth surface. This one's polished. But the inside's not. Then the inside, you have rough surfaces you can't get a tool into. You can't touch up. Sometimes we have never seen some of the features on the inside of these. Right, we don't know if they're rough or not. Then, but we test them and we understand relations and build off that. But people won't want to enter it because there's a lot of unknowns. Right. And it really, again, needed that philosophy from the ground up to say, this is something we're going to adopt. There's going to be pains. There's going to be unknowns. Then we're going to have to develop tools to account for some of these things that other people account for by just having a smooth surface then on everything. But we don't want to solve those issues, and we think we build enough understanding of the tech and the synergies there where you learn something on the test stand that you didn't know about the part, then because it's printed, and you account for it because of the printing. But not everyone else has thought about it in that manner, and we still get significant commentary from the other people in the industry that we kind of have a silly approach with this. but then you also see them complaining that, like, yeah, they had to retool their factory because they wanted to change their rocket size, and it's a super expensive effort, and they're really silly on connecting the dots, is my way to phrase it. Then, and I think they just at this point don't want to admit that they were wrong.
So the future of not just space, but aerospace and airplane manufacturing should be 3D printed, right?
We think really everything that flies will be printed, at least in the next 20 years. And the reason for that is that it again, from our perspective, just makes sense. And one of the main things there that I think everyone would understand is that there's value alignment. And there's value alignment in the sense that when you traditionally design a part, then there's this manufacturing optimization that happens where if you want to optimize it more and make it more lightweight, there's generally more manufacturing steps, then more time in the machine, more operators handling the machines and tendering these things, and that drives up cost. Then so you actually have this knee in the curve where you don't want to make your product any better because it drives cost up so much that it won't get adopted. For us, with the additive and additive by default, then you use less raw material, and you have less machine time the more lightweight the part is because you're literally adding on to it. So you're actually incentivized where optimizing the part more, you lower cost and you lower the time to get it. And that to us that just makes sense from our perspective where you want to improve the product over time rather than hitting diminishing returns on making it better. And with that in play, you could you'd want to make the high performance airplane. You wouldn't want to stop at a certain point because it got too expensive.
Yeah, freeze the design and then that's it. Yeah.
Right. So it opens up a lot of possibilities there. And again, aerospace is stagnated. Certain companies within aerospace are having their challenges in keeping costs down and keeping quality with that. We think something like the printing would really transform that in a way that would modernize aerospace manufacturing.
All right, so just to keep on time, Aditya, you had a question.
Thanks, Sasha. Thanks, Jordan, for the event. Nice talk. My background was in 3D printing at some point, so I have so many sub-questions. I'll keep it to one interesting one. So you mentioned on the insides there's going to be rough surfaces, understandable, because of the metal shrinkage and just the flow of it and stuff like that. How do you... what kind of rigorous simulation does it require for the fluid flow inside? And because obviously it's all pressure driven at the end of the day, the jet velocity and things like that.
Yeah.
How does it affect it? I think that would be it.
That's a good question, and hopefully I won't go into too much detail with it. But you have the fuel coming into the engine, and that's what we cool with. So it's a cryogenic methane, so a couple hundred degrees negative Fahrenheit coming into the engine. And that's what cools it. So the whole outside of the combustion chamber, which is the core of the stack there, is hollow, and then you have this ribbed structure on the outside in this jacket that this fuel is flowing through. And as it flows through, it's picking up heat because the combustion chamber is hot. The combustion chamber is around 6,000 degrees Fahrenheit. And you're cooling it with its own propellant. But over that wall that separates the combustion chamber from this cooling jacket, it's very thin, like ours we've printed down to about 10,000ths of an inch. And so your hairs are like 3 thou or something, so 3 hairs thick. Then in between that, you have 6,000 degrees on one side and negative 300 on the other. Then, so what happens in between is really where the magic happens on simulating that there's a significant amount of effort that goes into, making sure that when you do your first run of this, you don't just melt through that wall. Then, because that's painful on its own, but then there's challenges kind of across the board that it's not just that easy, because you're also then trying to tune what temperature and pressure the propellant is by the time you exit the combustion chamber and enter the injector, that your injector inlet conditions are correct. Because if your injector inlet conditions are wrong, then let's say your injectors are performing off nominal, and then your combustion's different, so instead of 6,000 degrees, you have 4,000. Then, so it's this huge closed cycle that's happening within that relation, and I could go deeper as far as how that affects the pumps and things like that on the vehicle, because if your combustion's off, then your pump performance is off, so your like inlet conditions are off. It's this huge coupled system there. And to the specific question on the roughness, the roughness is changing how the heat transfer performs on both sides of that wall there. Then we can see the inside wall, so where the combustion touches the wall, we can't see where the inside of that wall touches, or the outside of that wall technically, touches the cryogenic propellant. And that's where a lot of that uncertainty comes from, is that what's called cold wall heat transfer. there, and that's a lot of what we have to learn on the stand, where we've often tested engines in slightly different configurations than what you see here, with a setup different just to characterize that heat transfer very carefully, where you have significant sensor instrumentation along kind of the axial direction there to understand how much heat is the propellant picking up at every station there, because it's changing in temperature and propellant, or temperature and pressure, then which changes the heat transfer, which changes how much it picks up downstream, which changes the injector, which changes the combustion. It's this whole kind of fun chain there. And that's the stuff where it gets so complicated, just stick it on the test stand and figure it out, like stop with the analysis at a certain point.
Thank you. And just because I don't have anybody asking follow-up questions, can I ask another one?
Sure. Sure, and then we'll hop over to some more.
All right. So you mentioned pain points with CAD. Have you explored the use of generative CAD, where you have the requirements and have machine learning? I mean, it's a cliche word now, but certain set of parametric rules, and then have permutation and combinations of certain possible solutions of generative design. I think ETH, I mean, it's a part suggestion, part question. There are a few labs like ETH out of Zurich.
Yeah.
There is, I mean, they are exploring that generative design. So that will significantly maintain your fluid flow and all these requirements, but at the same time, like throughout design. Is that an exploration in terms of CAD pain points?
Yeah. Let me jump into it. I think, well, so the printing's the only way to really leverage the generative design or topology optimization, kind of the features that are designed that can't be traditionally manufactured, right? There's good synergy there. It is still a challenge to find a topology optimization software that's easy enough to use to make it worthwhile, especially in a fast-moving environment. And that goes into some of the design, kind of pressure we have in order to get parts out quickly. We've trialed a lot. We've given really strong feedback to a lot of companies that their software is a little too hard to use, and it's so slow to use. And so actually kind of painful to use, and you have to export from like your rev-controlled environment. And one of the things I hate when we do in an engineering workflow is like the engineers like copy-pasting things around and taking like a note or like a text file and copy-pasting values from that into a program. And that's a lot of what happens in the topology optimization workflows is they're super messy, super manual, and they're not done within the nice rev-controlled PLM environment, then which for aerospace is moderately terrifying, that you lose control of your config management as you go into these workflows. And they take so long. Like they're really hard on compute, and they're really hard for the design engineers to come up to speed on, because a lot of them have so much customizability that you need a software developer to write macros within their environment in order to get a part out. So you're actually kind of compounding on the number of people that need to be involved. And you also are getting something that takes significantly longer to get out, and it often hasn't been worth it to do that whole effort. I really want them to be, because it's something, you make these really cool parts, they look like internal bone structures and whatnot, but they're not in a spot where they're easy to put into a production work environment. And this is coming from me after talking about this whole like transformative change we've done with adding the printing. But it's not the right bet for us to really push now. Is that getting Flight 1 off next year is a pretty big deal, and it's actually been too much of a pain to get those workflows running, because I don't want to say running out of time, but like the time it takes to get them working correctly is enough that we'd actually have to push the flight schedule if we introduce those parts. So it's a later flight thing. But it's a fantastic tech. It's just not 100% yet to implement, or 100% there yet.
Let's get to the next question. We have people lined up.
Yeah, quickly. So Maynard Holiday from RAND, and then the Pentagon. So for your engine with the equivalent thrust, what's the discount, versus regularly assembled engines?
Oh, on cost?
Yeah. So when Musk came to us and said he could save us 40% on because he could land the first stage, that got our attention. So
Sure.
How do you get our attention?
Yeah, so our first product is Terran 1. We fly 1,250 kilograms to low Earth orbit. And we sell that for $10 million a piece right now. Then we've sold a number of those. At that price, the comparable vehicles are, let's say, Vega, PSLV. There's no current U.S. options. The closest was Delta II, and that's retired now. Then, so we cut down cost by a factor about 2 to 3 at that scale, and we bring it to a domestic option. So that's a big one. There, as far as some of the stuff we see on our roadmap, then is going into reusability. Then, so we have a next generation vehicle we'll be flying and kicking off about 2024 would be the current estimate on it. And that we actually expect to be what would be a properly designed from the ground up reusable vehicle. Then the Space Shuttle was way too expensive. Then and Falcon is an amazing product. Then as far as what they've done with it, but it's still designed as a flying tube with some things added onto it then to make it reusable. And as you see some of like the next generation architectures people want to do for reusability, whether it's Starship or New Glenn, they have a lot of features added onto them, like winglets for turning it into a lifting body, things that lower the reentry loads, lower things like that to get more reuse cycles out of them. Then, well, the challenge with those are non-symmetric. They're very interesting designs, but they're very hard to make. Then, and that actually drives up cost significantly. And so we do see something like the 3D printing as the core to be really how to get reusability, not just at a 4 to 5 flights on this vehicle, but how do you get 25? Then, because you can add features that make it actually a grounds up, reusable vehicle rather than a traditional vehicle with things added onto it, or some of the designs that are just very painful on a manufacturing side. So that's the first point then. And then the second would be on learning lessons from flight then, that with even these reusable vehicles, you develop them so that, they fly, then let's say like Falcon, and then you learn some things when they come back, then things that are sometimes obvious, sometimes not, on what's fatiguing, what's breaking. How do you want to account for that? Then you're going to retool your production line in order to account for the things you're learning when you're flying, because you learn these things once you already have a fully built out production line in order to do the ascent part of the missions. Then, so for us being able to actually account for things seen in flight, then, which are the things that are often really painful to respond to, you want a flexible manufacturing line. So the first time it comes back and you realize this is cracked, this is nearly broken, this is falling off, then you account for that, you fly it, twice, you bring that back, you understand what's breaking next, and then, the next one flies, 5 times, and after that, you keep going. But I think without something like a flexible manufacturing line, a lot of the promise for getting to these, 10 plus reuses, then is going to be extremely hard and take a long time, and because you can't account for the things that are coming out of your fully developed factory. And that's my thoughts.
All right, Jeff.
Do you do any post-welding heat treatment of larger structures such as tanks? And if so, can you describe difficulties on quenching a 14-foot diameter tube?
No, we generally work with the alloys that don't need something like that as far as very high temperatures. So we'll do like an age, then, but we won't do an anneal. Then as far as at that size and scale, then, because we don't want to have the world's biggest heat treat furnace. Then there are big ones out there, but there's challenges at the scale as far as getting symmetry in the cooling and having something that large, supporting itself under its own weight, then at that temperature. Then, so there's a lot of we've done on an alloy tuning side to get there, but it's definitely something we keep in mind is that on those downstream steps, we'd rather not. Then just because it's a logistical nightmare to work with some of that stuff, and we've had the thought experiments on like, okay, if we have this 30-foot tall, 12-foot diameter, 3,000-pound fairing, then and we need to heat treat it, then and quench it specifically, then like who could do that, and how would you do that effectively as far as very rapidly dropping this very delicate fairing into a bath of water or whatever you want to drop it in. So we've thrown all that out. Again, sometimes losing performance along the way then is that some of the materials we're not 100% happy with the it's basically like a T5 temper is where we get to, like settling with a T5 temper is not great then, but it's also, you're flying a chubby launch vehicle then and fairly low performing, but can adapt to change and introduce some of those things as we figure them out or get new materials in quickly.
All right, Ariel.
Thank you for your talk. So I'm curious about your 60-day deadline or, I guess, goal. And I was wondering if that came from, say, theoretical constraints for how fast you can 3D print an engine at that scale or some other factors.
Yeah, the original estimates, and they've evolved a lot as we've evolved in maturity on the product and then, understanding some of the other limitations of the tech. Then, but even right now, we can do about a foot of height on the big printers a day. Then the vehicle's 105 foot tall. We have 4 of them right now. So even with the current fleet of printers, you theoretically could get an entire launch vehicle structure out in about 25 days. And then we're not 24/7 right now. We don't have that high of uptime as far as 100% there. But it's enough that that actually is starting to make sense as far as getting the structures out. There's a decent amount of downstream processing we have right now, and not everything is as integrated on a number of parts printed in one structure as possible. So all that's in downstream processing, but we see the way that the printers on the smaller scales, the powder bed printers, growing, that a lot of the things, even like the bolted flanges here, will start going away. Then, so less assembly steps, more complete products coming out of the printers. And then as we work our roadmap of features we want coming out of the big printers, more and more will be coming out of those. Then, and then there's optimizations to have as you hit diminishing returns on adding more to the printers, on either automating the downstream fabrication, then or just simplifying that process that, that is already kind of in. It's reasonable to say that those would start to come together over the next couple of years to hit that cadence.
Thank you.
All right. Michelle.
So it sounds like due to the scale of what you're working with, you've had to drive a lot of innovation out of necessity. I'm thinking things like the sensing as you print and the feeding of the material and things like that. Even though it's out of necessity for you to accomplish what you're trying to do, it seems like that is very applicable to smaller scale things as well and can help reduce costs and bring better quality into those kind of things. So have you thought about licensing, and like trying to see how you can monetize this innovation beyond building, the end goal?
That's a good question. It depends. It's a little bit of a resource allocation side right now as far as what do we have the resources to support as a company, including like Flight 1 on the rocket side is what makes the most sense. Then, but we're having a lot of conversations on the different verticals as far as areas to go into. And some of the ones that are more obvious to us are the ones that are more on, commercial aviation, defense, things like that. Then very highly integrated, high value products that would leverage the complexity reduction of what we're doing. But it's not necessarily on a piece part side or on a licensing side where we would actually, I think, need to make, as far as the same way that we've had huge amounts of adoption or friction adoption in, let's say, our former employers on adopting the tech. If we had one of our printers out there and someone trying to get the full value out of it, I don't think that would happen unless they had a lot of the mentality we have on how to get the printing to really transform the company around it. Then, if that makes sense. So the licensing isn't something that is really on our radar today as far as wanting to license the tech, but it would depend on the specific area. Some of the ones that are less in our wheelhouse, like outside of aviation, outside of defense, there may be things, and I'd be happy to hear more on those, because we generally don't think about those that often. Then, but again, on alignment with the tech, the super lightweight things that are like, generally super high price point, which is what can really push the tech forward then because of the amount of money in those industries, are where we've targeted first.
All right. The awesome Young.
Okay. So a couple quick questions around this process as a whole. So like a lot of the old school aerospace programs, they leverage these existing parts. Because of the fact that they're really well characterized and tested, and you're able to use as much commodity as you can, piece it together, and meet the engineering spec in which you set out to do, in this case, hopefully successful launches, or as many successful launches as possible. The up integration of these individual components, I think, definitely simplifies the supply chain significantly, but at the same time, you're kind of incurring a lot of engineering depth in the highly specialized areas, whether it's pumps, nozzles, whatnot, and also the qualification of the process, reliability projections. So what is the idea around the validation of the product to hit the same level of reliability expectations for successful launches that's viable commercially? Because if I'm a customer for a rocket like this, I want my payload to make it up successfully. What are your thoughts around that?
I'd say it's similar to part of what I was telling Sasha on specifically like where do the risks come from in the value chain, and significant amounts of the issues on rockets historically as far as things that have brought missions down or non-successful orbit insertions then have been on things that were either manufacturing mistakes or sometimes design mistakes where things were missed on part performance. Then are things like coupled system interactions that were very hard to model. Then are very hard to understand what was going on between two systems on the vehicle. Then so I think all of that starts to get reduced as you lower the number of parts on the vehicle. then, and even if you understand each specific part less, it's those coupled interactions, it's the manufacturing step reduction, then that really starts to get you the reliability. And our customers are on the same page there, that the ability to understand kind of the product as a whole, and it's a little counterintuitive, I'd say, even as I explain it, that the ability to understand the product as a whole is improved, even if each individual piece part's understanding is worse, because, again, you can't see the inside of these, but we'll do things like CT scans, we'll do various kinds of inspection to understand the internal structures, even if we never get the chance to see them visually.
Yeah, just a quick follow-up. So as you up-integrate these functionalities, the system as a whole, even though the parts are less, their interactions becomes much more coupled and complex, where, like, instead of just testing my valve or just testing my nozzle, now it's kind of all in one. So how does validation in that context work? Because now twisting a knob doesn't necessarily correlate to one particular subset of the performance, and it's the entirety of the rocket.
That's fair, and I'd say that's actually a level of integration that we haven't even gone yet as far as combining these. Then that each of the components we make is still testable on its own. And that's a big thing, especially going into Flight 1, that there's certain things like, the valve housings could be printed into the side of the engine. But then it's like, how do you test the valve independently? Then how do you test the engine independently? And that's a level of integration that is a later optimization. Then as we understand more of, let's say, simulating or more of the empirical correlations for our specific products, then that none of what you see here as far as the pumps can be put on the test stand independently of the valves, independently of the combustion chamber, test it all separately. We have testing infrastructure at our Mississippi site for all of that. Then that you are very right in your point that the more those become coupled on a manufacturing side as far as within one body, then the harder independent testing of each individual area becomes. And that's an area we want to tackle, some through, again, better understanding of the designs as we mature as a product, but also some of the things as far as even simulation. Then where we're understanding more on how these parts behave, within the combustion environment, things like that, so that we can actually simulate some of those interactions better and understand if we're starting to get to a point where there'd be risks there.
All right, best for last. Jen, what do you got?
I'm Jen, and I used to work in additive manufacturing at Carbon. And I was wondering, I love your vision of being able to take a 3D printer up into space and print spare parts. I think that's awesome. I was just wondering, I don't know of any additive manufacturing techniques that work in like microgravity environments, and whether you have tried that or how you think about those techniques.
Yeah, we haven't tried yet. Then it is something to map out, and part of where we're steering a lot of our government partnerships is things like that, as far as being able to fund, let's say, projects that support NASA human exploration on the moon, then which is clearly a big direction ongoing now. And how would we start prototyping the printers there? Like, we wouldn't send one of our full-size printers. It would be demonstrating some of the smaller testing. There's some advantages of the print processes that, they sometimes leverage the zero-G environments. Like our specific printing process we do at a large scale can be done, it can be done in kind of how you saw it here. It can be done sideways with more and more controls on it, and it can be done upside down, then, which is tricky then with it. But some of the features you'll even see on the, they call it the hot tub here. There's a big printed dome. I don't know what they do here at night. But there's a printed dome up front, and you'll see some of those features were actually printed on it near horizontal. Then I think that dome, which is about 2 years old, was, that's before we could go kind of full 90, and now we can go a little below horizontal there. But we've done things with weird kind of gravity vectors on them, and that has to do with how you control the print process, how hot it is, what the surface tension is because of that, and how well that liquid pool wants to stay on that wall. But there are ways that it can be done with that, and it actually gets easier if you don't have that gravity vector moving around. You can tune it a bit better, and you're relying on the surface tension to keep that puddle there. And I would, kind of prefer, but it's in, hindsight's 2020, but I'd say I'd prefer to get rid of that gravity on it so that we have less variation as we do different kinds of features. Like, you can rotate the print heads without seeing variation because of the angles and having to account for that. It's actually a real pain to have to account for variations in like melt pool flow with different print angles. Then there's certain things that get harder, like we currently do arc depositions. You need an inert environment around the arc. So we generally would have to do something within like a closed environment then, which I'd rather, it's one of those things we need to figure out in the coming years as far as what of the architecture elements we're doing today scale well to that off-planet vision, then in which are the ones we want to tweak. Like we used to, in the first generation of the printers, we actually, we did a switcheroo on the playground, guys, as we were fundraising that we used to do laser printing then, and that was, high power diode lasers. Then our highest power one at the time was 11 kilowatt. Then we switched to the arc method. Then because it made more sense on cost at the time, on performance, on controllability. Then but we switched right around 2 years into the company and completely pivoted on a back-end architecture on the printers because we learned so much with the lasers. But the lasers are much more keen to open atmosphere environments than if we wanted to go through them, because you're not relying on that plasma then to do all of your heat transfer into the pool. And so that's a direction we could go as well. There's different challenges with having high power diode lasers as your power source when you're off planet. And I don't think anyone's ever flown, an 11 kilowatt diode laser to the moon. That would be a fun toy. Don't point it back at Earth. But that's kind of the direction it would go, is looking at what architectural elements can operate well in that environment from the current setup and see if it's worth the switching cost to try something else at this point.
All right. Well, this has been fascinating. I'm sure I speak for everybody here. Thank you all so much for coming. And Jordan, it's been a pleasure. Yeah. All right. Thank you all. Come again. We do this all the time. All right. Oh, you can.